Hello, welcome to numerical ship and offshore hydrodynamics. Today is the lecture 24. Today we are going to discuss this following topic. We have to discuss about the how we can make the influence matrix in when you are solving this source panel method, right. We know that how we can make this influence matrix when we solve that problem in finite fluid domain, and where you can use the source dipole panel method, but here we are going to do with the source panel method. And then again we need to find out how to convert this integral equation into the algebraic equation. So, these are the keyword that we are going to use to get this lecture. Okay. So, now let us start. Now, as you know that when we are doing the integration, that integral equation that phi, that any point in the this p point p, let us say called the field point. Now, at this stage you should not have any confusion about what is called the field point, what is called the source point. So, this field point p could be any point in the domain, and then we placed it on the panel. Now, so as you know that we place this field point at the panel I, and then we need to integrate that all the panels in the inside the boundary. I mean, in case of a Rankine panel method, then the whole free surface plus body, and in case of this Wamit type solution, in our case it is the body. So, it means that I discretize the body, right. And then we need to perform the integration over the body. So, I just take one arbitrary panel j, right, then j should be runs from 1 to n, like, right, fine. Now, if it is so, then this is how actually we are going to do with the form the influence matrix. Okay. Now, here we know that how we can do this for the one point Gauss quadrature rule, but here really we are not going to use any kind of this one point Gauss quadrature rule. Here we are going to use sometimes the 2 point Gauss quadrature rule, sometimes 3 point Gauss quadrature rule, sometimes of course 1 point Gauss quadrature rule also we are going to use. But now we have to understand very clearly how actually we can convert this. Now, remember in our case, if I let us go back to our this, just let us just for your reference, if you remember that in case of this 1 point Gauss quadrature rule. So, and now I am just going dealing with let us take the source panel method and try to figure it out. So, now in case of a source panel method, it is that this is nothing but this alpha p. Now, in case let us not take alpha p let us take alpha p equal to 1, and this 4 pi let us bring back into the right hand side of the equation. Now, if it is so, then alpha p is nothing but for the source panel method is sigma into g into del s. So, when you have this the surface S, and now if you differentiate with respect to n, then the left hand side become del phi del n into p, and which is nothing but here sigma will come out, and over the S it is del g del n into d s. Now, if you remember, if I try to do this with our lower order panel method, of course, lower order panel method, and then if I take this 1 point Gauss quadrature rule, if I take this 1 point Gauss quadrature rule, then our what is our strategy? Our strategy is, suppose this is my panel. So, this is my panel, right, and then in this panel let us take this is my ith panel, right, this is the source the field point p, and these all are the jth panel where you can think of the source point j, right. Now, here del phi del n is equal to of course V n. So, here I just I just write it is V n for the ith panel. So, I call this is V n I. This is what is I am taking in my left hand side. Now, then if you remember in the right hand side I should write it is, now it is runs over j is equal to 1 to n, right, where j not equal to I, that is the same thing, that is what I said, right. This equals to sigma j into del j, it is I comma j by del n for the jth panel, and we need to multiply by the d s j. This is how I should write down my influence matrix, and this is also of course the sigma j. And when I equal to j, this is we have to take plus half of sigma j, that is what is that is what actually we have seen from the last class. So, this is how we are going to discretize the whole thing, right. So, then it is very simple for in case of a one point Gauss quadrature rule, I am taking the functional value at the centroid of the panel and then I multiplied by the area, right. So, it is very easily it is sigma j and then it is and in fact call it is a I j, where we can so where I can write that when a I that should be is equal to half. So, this is how actually very easily we can do this, right. This is how we are going to do it for our one point Gauss quadrature rule. But now, this is not one point Gauss quadrature rule. So, now here we are not doing this way. Now, if you remember this, what in the left hand side, let us start from here, it is del phi by del n, this is for the of course, for the ith panel, and this should be as you know it is half of sigma I, that you know, then plus now what I am doing over here, this panel, now here let us say this is your ith panel where I can get this half of sigma I. Then what is doing now here in this panel, let us say this is a particular jth panel. So, in this jth panel what I am doing as follows, I am assume in this jth panel my sigma is constant, that is what we are doing for the for lower order panel method. We are assuming that for each panel your velocity potential phi as well as the strain sigma is constant for a single panel, different for the different panel. Now, while doing this integration over this jth panel, since we are assuming now if you take this, let us say I am just taking out this sigma, it is a big, this is my jth panel. Okay. Now, in this jth panel what is happening, that sigma is at the center of this panel and we call this as your sigma j, right. And then, but we need to integrate this. Earlier what we are doing is that at this point only we try to find out the functional value, that is del j I comma j divided by del n, that is what I am doing at the centroid, and now I multiply this by d s into j, that is what the strategy for one point Gauss quadrature rule. But now here we are not doing this. What we are doing is as follows, I am writing this summation j equal to 1 to n, and of course, this j not equal to I, this till this point everything is same, but then what I am doing, I am taking sigma j out of this integration sign, because sigma j is constant over that panel. However, we need to perform this integration. Okay. So, it is, let me write in bigger way, we need to perform this integration over this panel, then it is like this. Now, it is clear. Now, the difference is earlier I am using the functional value multiplied by the area and I am getting it, but now we are performing the integration. We are performing the integration over this panel, and this would be the numerical integration. It could be, if it is a one point Gaussian quadrature rule, then it is similar to this. How otherwise it will be different. So, that is why now let us go back to our main slide. So, here that is why I am writing that this is this in panel J, that is it is actually it should be sigma j. Okay. So, let me just correct this one here. Here it is actually it is sigma j, right. So, now this actually what I am doing, that I am taking out this sigma from the out of this integration sign, right, and then I am performing this whole integration. Okay. So, this is actually we are going to do, right. Similarly, if we consider this other part, actually this one where we just integration over the g, where the del phi del n is the del phi del n j, basically that is the again is a constant over a panel. So, it is coming out of the integration sign, and then this integration is only g into over this panel a j, and then we are getting this right hand side this one. Let us see that how the other part we are doing. Now, if you look at this second part, then once we know this sigma, right, if I solve this equation, I get the equation for the sigma. Now, remember this equation I need to replace this over this sigma into g into ds. So, then these things we need to replace over here. So, after solving this equation, I am getting the value for sigma. Now, once I get this value for sigma, but then again I need to perform this integration also, right. Now, here this sigma is known to me, right. So, therefore, essentially my integration becomes here. Now, this let us say for the second part. So, now my integration is become only in this panel, it is integration of g into ds, right, because sigma is again constant and I take the sigma outside the integration sign. So, essentially this integral I can call is I 2 is nothing but my sigma j into integration over this s j into g into ds j, and then we can now you have to repeat this for all j. So, I just write that j equal to 1 to n, and this now everything is known to me right here, because my sigma is already known from my previous equation. I solve it, I get it, and then here this in integration this g is known to me. So, everything is known to me. So, essentially I will get a number. So, I can call this is for B I for the ith field point, right. So, now here let us go back again and let us see that if we understand this equation correctly or not. If we integrate this the first equation, this equation if I integrate, so then I have it is of course the sigma j into a I j, right. And now, once I know the value for sigma over here, so then I substitute the sigma here. So, once I substitute the sigma over here, and then I have this the second part the integration. Now, everything is known to me, right. So, therefore, I can get a number and this number is called B I. So, this is actually this integration scheme for this frequency domain panel method, right. Earlier we have only single equation where that sigma and phi, I mean that means g and del g del n both are there, but here first I do the integration for del g del n and then I can get the influence matrix, okay, which is sigma j I j, and then once I get this value for this sigma, then I can use this sigma to get the value for phi, right. So, this is the scheme. Earlier in our source dipole method, in single equation we are solving everything. Now, here for the only source method, first we are solving for sigma, and once we know the value for sigma, then I use this value and I solve for phi. So, this is the only difference. Okay. So, as I said that, so once I solve this equation, then actually I am getting this equation Aij sigma j equal to 20, and I know how this Aij is basically the influence matrix, and once I have this influence matrix I can get the value for sigma, and once I know the value for sigma, then I substitute this in the Bij, right, and Bij we know that how we got this Bij, right. In this equation we are going to get this Bij value. So, once we have this Bij, we can solve and we can get the value for psi. Okay? Fine. Now, once we know the value for psi, then how actually I can write the added mass and the damping, and of course, the exciting force. Now, here in this equation 22, I write 3 expressions, right. The first expression for the added mass, the second expression for the damping, and third expression for the exciting force. Now, let us see that how actually I get these values. Now, if I go here, I know the radiation force is nothing but Aij into x double dot j plus Bij x dot j, right. We know that, right. It is added mass multiplied by the acceleration and then the damping multiplied by the velocity. And also if you remember, when I write this the boundary value, I mean the boundary conditions, that time we are taking one assumptions that I am for the radiation force, of course, we are solving for the radiation force. I am assuming that I am oscillating the body in the direction of j, and amplitude of the oscillation is 1. So, therefore, here I am taking that since I am oscillating the body with a unit amplitude, then I can write the equation as x j equal to 1 into e to the power I omega t. Now, once I do that, then easily I can get the velocity and the acceleration. So, velocity will be I omega into e to the power I omega t, and if I differentiate 2 times, it will be minus omega square into e to the power I omega t, right. Now, I substitute this into this radiation r. So, once I substitute this, I just substitute x dot equal to minus omega square. So, I just substitute over here and I substitute x g equal to I omega. So, therefore, I can get my radiation force in terms of omega square A I j minus this, right. Now, here this is how actually I can get the force. How I get the force? So, now, so solving that equation, right, solving that equation, I mean solving this equation, I get the value for phi k, right. So, now, once I get the value for phi k, the next job is I am going to get the pressure, that means the radiation pressure field, right. So, therefore, if I do that, now I assume my phi is harmonic. So, I assume the phi equal to phi x into e to the power I omega t. Now, if I make the the pressure is minus del phi del t. So, definitely I am getting minus I omega rho into phi j into e to the power I omega t, right. So, then how I get the pressure? So, now this pressure if I integrate in the direction of I, so I get the force in the direction of I, right. So, I oscillate the body in the j direction, right. If you have confused this, just I mean refer to my previous lecture, right. When I say that I can oscillate a body in some arbitrary mode j, but still I can expect some force along the direction of some I, right. That means, I am oscillating the body in the heave mode, but still I can expect some moment along the pitch, or I can oscillate the body in the pitch and still I can expect some kind of force in the direction of heave. So, let us take I am oscillating the body in the pitch. So, therefore, I have to solve this equation where phi 5, right, and I solve this equation for phi 5 and I get the solution for phi 5. But then if I need to find out the force along the heave mode, then normal has to be 3. So, therefore, I am getting f of 3 5. So, the second index refers to the mode I am oscillating the body, and the first index refers to at which mode I am going to get my force. Now, here, so since it is the ith mode, so I have to multiply it by the I. So, therefore, my force becomes minus I omega into integration of n I phi j into d s. Now, remember this is definitely a complex number. When you do that, you are definitely going to get a complex number. So, now I just equate these two. So, I equate that omega square a I j minus I b omega b I j into e to the power I omega t into the right hand side where I am going to get the force, right. So, now if you now relate the real part and imaginary part of it. So, then you understand that the real part goes with the added mass and the imaginary part go with the damping, right. So, so that is why that I am getting the added mass equal to rho into real part of minus I by omega, because if you divided it by omega square, so it is become minus I by omega into n I psi j d s 0. Now, here the d s 0 refers to the linear feature, that means that it is z equal to 0, right. When you do the non-linearity, that time we need to integrate over the S b, that exact weighted surface, but here I am doing the integration on the mean weighted surface, right. Now, if you confused with what is the mean weighted surface and what is the exact weighted surface, just again let me explain you. Here the mean weighted surface here, like if it is the, let us take the body like this, then the mean weighted surface is basically the line z equal to 0, and then exact. So, this I refer for this under this mean line, this weighted surface I refer to S 0. But then if I consider this wave and if I take let us do this in the red, if I do this exact. So, this is called the exact weighted surface, and if I do this integration, normally we define by S of b. Okay. So, let us coming back to the slide again. Now, here if you see that I am doing with the mean weighted surface, that is why I am multiplying by the S 0. Okay. Fine. Okay. Fine. So, now similarly this f I also, now it is well understood that it is the similarly it is also the same way I am getting the sigma. Now, sigma 0 is nothing but your the Fruit-Kirchhoff pressure, right, Fruit-Kirchhoff force, and 7 1 is nothing but your diffraction force. So, once you solve this sigma 0 and sigma 7, you multiply it by the normal n I, you will get the value for f I. Okay. So, this is how I am getting this added mass A I j, the damping or A I k, if it is. So, here the notation is k, and then the damping B I k. So, here in this case actually in kth mode I am oscillating the body, and then that exciting force the right hand side F I. So, this is the overall the process to get the value for this quantity, added mass, damping, and then the exciting force. Now, once I get this, then I substitute this value in the equation of motion, right, and then I can get the value for the displacement. Okay. And how we are going to get this? How, I mean that putting this value into this system of equation and getting the value for displacement and velocity, those things definitely we are going to discuss, but not today. Now, today what we are going to discuss is that what is the complexity or the challenges, I mean to compute this A I j and then B I j. Now, if you look at here, there is a two challenge. The first challenge is to get the value for 1 by r plus 1 by r dash. Now, when r equal to 0, that means when the source panel or field point coincide together. So, that time you can have a difficulty to get, and also you have a nevertheless that we have the difficulty to get the value 1 upon r anywhere, right. Forget about this close, like you have to set that what integration scheme one should follow to get a convergent solution anyway. But again if you look at the second part, then you can see there are 3 term k 0, y 0, z 0, that means there is a Bessel function is there. Already we have discussed that already this integration range is 0 to infinity, is a improper integral in a mathematical. Let us forget the maths part, but at least we understand this integration, that means it is a infinite sum. If I do that in numerically, I have to do a infinite sum. Now, once we do this infinite sum, then it is a time consuming first of all, and second thing, it may converge, it may not converge, right. And if we get a non converging sum, then the solution completely wrong. Second one, again we have these Bessel functions of different kind. All these functions are again is a infinite sum. So, again to compute these values also sometimes you have to make sure the range is always in a convergence, like your value for k 0, y 0, z 0 all are convergent, right. Now, I will show it is not always the case, and let us see. Now, here so as I said, the major difficult task to complete highly complicated free surface Green's function, right, and then it is highly oscillatory and frequency dependent in nature, right. And also as I said, this is the improper integral, that whole integral is 0 to infinity. So, it is a improper. So, we have to look for the convergence, right. Now, here I say that not always it converges. If you look at this graph for k 0, now when you can see that when it is k 0 going towards 0, then you can see the functions becomes infinity, and similarly same for y 0 also, right. Now, thing is that it is asymptotically go to infinity. Now, thing is that these are the complex things that we need to deal with, right. But we are definitely we are, so say we need a strategy to integrate the Green's functions. So, what are the strategy to get the Green's functions, like this the whole part 1 by r as well as this free surface Green's function, that we are going to cover in the coming lectures, right. So, just for a brief, that what we are going to discuss in the coming classes, initially we started with the Rankine method, and then we have to see that how this is based on the distance between the source panel and the field point. We need to find out the different scheme for it, right. For example, we have to discuss something about this characteristic length, what is the meaning for this characteristic length, and also based on this characteristic length we are going to discuss what are the integration scheme, right. So, those things we will going to discuss from the next class. So, for today let us stop over here. Thank you.